Good afternoon. Welcome to Project Jigsaw, Under the Hood. My name is Mark Reinhold. I work in the Java Platform Group at Oracle. This is the third of three presentations my colleague Alan Bateman and I have given here at Devoxx this week. This is the most advanced one. In this one, we're going to take a deep dive into essentially the science of the module system that we've designed for Java 9. Just a quick poll, how many people were in any of the earlier sessions, including the university on Tuesday? Excellent. Okay, so you've all got at least some idea of what's going on. How many people have downloaded and played with the highly flammable, very dangerous Jigsaw early access builds? Okay, good. How about just the regular JDK 9 early access build, somewhat less dangerous? All right, excellent. How many people know why there are not version strings in require statements? Okay, then one of you can answer the question when it's asked. Okay, so Java 9 at a glance. In Java 9, the main feature, as you know, is a module system that helps us write code that's more reliable and maintainable. We've used the module system to turn the monolithic JDK into the modular JDK, breaking up the old rt.jar file inside the JDK into dozens of reusable modules that you can configure as you please. Java 9 also has small enhancements to the Java language and larger enhancements to the standard libraries, plus new tools and a search box for JavaDoc and the JShell tool, which is really cool, by the way, and tons of other stuff, which, of course, I'm not going to discuss here. Project Jigsaw is a project led by Oracle in OpenJDK. It's the container, essentially, for all of our work building a module system and applying that module system to the JDK itself and working on the tools to support all of this and so on and so forth. We're standardizing the module system in the Java community process in JSR 376. We're also standardizing the structure of the modular Java SE platform in the JCP through the umbrella JSR for Java SE 9. So when you use Java 9, you will always be subject to the rules of the module system. There is no escape. That's what under the hood, that's what is under the hood, and it's what most of this talk is about, though I'll touch on some aspects of the modular JDK near the end. This talk has 4 parts. The first part explains how the module system works with the Java language and the VM to improve the reliability of code. The second part is about migrating to modules. You've already heard some of that in the advanced talk. The third part explains what the module system is fundamentally capable of beyond what you can express in the Java programming language. And the fourth part is a bit about the road to Java 9 and some of the things you should watch out for. So, part 1, accessibility and readability. Everyone knows the hierarchy, the ranks of accessibility in the Java language and virtual machine. It's simple to understand, it's easy to use, and it's strongly enforced by the compiler and the VM. And this is what we've had for 20-odd years now. It has a big weakness, however. The only way to share code between packages is with public, but then you're sharing with everyone. So it's not that surprising that package friendship in one form or another has been requested many times over the years. One principal goal of the module system is strong encapsulation, to allow a component to declare which of its public types are accessible to other components and which are not. In Java 9, the module system has therefore extended the accessibility model. The lines in italic here are the new levels of accessibility. Reading upwards from the lowest italic line up, you can arrange for public types to be accessible only within their module. You can make them accessible within their module and to other specific modules by name, or you can make them accessible to everyone. Now, as usual, migration has driven a lot of the thinking behind this design. We want to make it easy to place an existing package into a module and immediately give it the benefit of strong encapsulation We don't want each and every public type in a package to have to opt in to strong encapsulation. This is why we haven't introduced, say, a module access modifier that you could sprinkle inside a regular Java class file to say that it has module scope. That would require changing all existing code in order to leverage the module system. So public types in a package are not accessible outside the module by default. And here's a really important point. Public in a type declaration no longer means that everyone can access the type. Okay? Public in some sense is no longer public. So what happens if someone tries to access a public type that's not accessible? Well, here's an example. This is Glassfish 4.1. It doesn't start on JDK 9 because the VM throws an illegal access error. The error message says, if you read closely, class com.sun.enterprise.security.provider.policy wrapper in module unnamed module cannot access class sun.securityprovider.policy file in module java.base. Don't worry about the unnamed module part. We'll get to that later. The point is that the policy file class is declared public, but since it's a JDK internal API, it's now accessible only within the java.base module. Sorry, Glassfish. You've got to go find an alternative API. In Java 9, modules are first-class program components, like classes and interfaces. Here's the declaration of the java.sql module that contains JDBC. It's in a file called moduleinfo.java in a directory named after the module. The compiler treats it like any other Java source file and translates it into a moduleinfo.class file, which you can put in a jar file as normal, and the result is what we would call a modular jar. The package hierarchy exists in the same directory as usual. So moduleinfo.java is outside all of the packages in the module. It's the job of the module declaration in that file to say whether a package is strongly encapsulated or not. So it's really easy to get strong encapsulation for a package. You just don't mention it in the module declaration. To allow other modules to access a package, or more specifically to access the public types of a package, you add an exports clause, as shown here. You can export to all other modules, or you can say exports to a specific set of modules by name to give access only to your friend modules. Now at compile time, JavaC prevents code outside of the JavaSQL module from accessing the public types of any packages except for those three listed here. You get the same compile time error as when you try to access a package private type from outside its package in Java 8. And at runtime, this is all about fidelity, at runtime the VM throws an illegal access error, as we saw with the Glassfish example a moment ago. All right, let's dive into the VM more deeply. Traditionally, accessibility in the Java platform is about who is doing the accessing and what is the public protected private flag on the target class. At runtime, the VM uses the class loader of the accessing class to find and load the target class, and then the VM checks the flags on the target class. This is what we've been doing for 20 years. Because the VM relies on class loaders, people can create class loaders that only know how to find and load classes of certain packages. In effect, loaders can isolate one package from another. In the top picture here, class P.C is trying to access class Q.D. The loader for P.C knows how to delegate to another loader for any class in package Q, such as Q.D. Only when that other loader has loaded Q.D can the VM then check its flags to determine if P.C can access it. In the bottom picture, the loader for P.C has no idea where to find package Q, so no access to Q.D is possible from P.C. Now, technically, this is not a failure of accessibility because the VM never even gets the chance to check the flags of Q.D. Instead, it's a failure of visibility. Q.D is invisible to P.C. Still, the effect is quite powerful and useful. If the class loader of the accessing class can't find and load the target class, then it doesn't matter if the target class is public or not. It's effectively encapsulated. Whoever sets up the class loaders sets up the encapsulation. Encapsulation based on class loaders, however, is not strong encapsulation, hence the sad face here. It relies upon packages being carefully apportioned into different loaders, but that isn't how the JDK works. Most code in the JDK is loaded by what's called the bootstrap class loader, while code on the class path is loaded by the application class loader. Spinning up lots of loaders for all of this code, if we were to have one loader for every module in the JDK, would be a compatibility nightmare. And in any case, there's no actual isolation. You can circumvent class loaders by getting hold of reference to Java-Lang class objects. Once you have a class object, class loaders are completely irrelevant, and it's impossible to stop references to class objects from being passed around. Strong encapsulation is about being able to prevent access even if the accessing class and the target class are in the same class loader, and even if someone is using core reflection to manipulate class objects. Let's assume that multiple modules are somehow mapped to the same class loader. Can class P.C in module X access class Q.D in module Y? Recall that another goal, the other principal goal of the module system, is reliable configuration, to replace the brittle error-prone class path mechanism with a means for program components to declare explicit dependencies upon each other. So in order for P.C to access Q.D, not only does module Y need to export package Q, but module X needs to explicitly depend on the module Y. The formal name for depends on, when we think about it this way, is readability. Readability underpins accessibility in the Java language NVM. The accessing class P.C must be in a module that reads the module of the target class, that module is Y, and the module containing the target class, namely Y, must export its package Q to at least the module of the accessing class, and maybe to all modules in the system. You can see that accessibility is essentially a two-way street. X reads Y, and Y exports package Q to at least X. Accessibility is independent of class loaders, just as before the module system. This is important for two reasons. First, it means accessibility works at compile time when there aren't any class loaders. Second, it means you can reason about accessibility based solely on requires and exports clauses in module.info.java files. There's no need to worry about the class loaders in existence at runtime, how they were configured by code that you might not even know about. In fact, the exports part of accessibility is pretty straightforward. A package is either exported or it isn't, but on readability, there's a bit more to say. When you depend on a module, you depend on a hopefully coherent collection of packages that it exports. In some sense, those packages are kind of some abstract interface of the module. Inside the module, hundreds more packages might sit, strongly encapsulated, waiting to help implement that interface. And more than that, when you depend on a module, you indirectly depend on all of the modules it depends upon. For example, if you depend on the Java Activation module with its 35 classes, then you also depend on the Java Desktop module with its, guess what, 5,835 classes. If the watchword for Java 8 was functional, then for Java 9, the watchword is transitive. You should think in terms of the set of modules needed transitively by your application. The indirect dependencies can be as important as the direct ones. Let's see how readability handles this. I'll use an example of readability from the actual graph of JDK modules. The java.sql module that holds JDBC requires the java.logging module that exports the package java.util.logging, everyone's favorite logging API. This lets code in the JavaSQL module access the public types of Java util logging, such as the logger class. You can see that in some code in the JDBC driver manager is here newing up an instance of logger. What if the API of the JavaSQL module, rather than just its implementation, wants to use the logger type? For example, the JDBC driver interface wants to return a logger with this get parent logger method. Let's look at this through the eyes of an application module that uses JDBC. We'll creatively call it MyApp. In order to use the driver method that returns a logger, the MyApp module not only needs to read the java.sql module, but also the java.logging module, which exports logger. It would be a pain if the developer of my app had to remember to say requires Java logging when using the API of Java SQL, hence the frowny face. Well, there's good news. The Java SQL module can take on the responsibility of remembering. Look at the Java SQL module. It now says requires transitive java.logging. The word transitive here means that anyone who reads the java.sql module also reads the java.logging module for free. The MyApp module doesn't have to bother with requires Java logging because it reads Java logging thanks to reading Java SQL. Happy face. This is called implied readability, and it's very powerful. It's powerful because it lets a module be refactored without breaking its consumers. Refactoring modules is going to be as important a thing as refactoring classes. For example, suppose that Java logging has some auxiliary packages that we'd like to start shipping in a separate module, say log extras. The Java logging module can say require transitive log extras so that my app, which implicitly reads java.logging, also now implicitly reads log extras. My app would be completely oblivious to the fact that this is happening. In essence, the readability model supports a form of downward decomposition. Any module you read can be decomposed into new modules, and readability of the new modules can be recovered with the requires transitive clause in the old module. So if you think about it, the definition of reads must be recursive, right? A module X reads another module Y by requiring it directly or by reading some third module Q, there's the recursion, where Q says requires transitive Y. And now that X reads Y, Y can say requires transitive for some other module, and X will read that too. Now, some care is required here. Once people require your module explicitly, you can refactor it as much as you like, but you cannot delete it. There's no way for a module to stand in for another by taking its name as an alias. If someone requires X and X is deleted, then the module system will not start. A related point is you cannot ever effectively remove a requires transitive unless you absorb that other module completely into yours. The use of requires transitive is essentially expands the surface area of the effective API of your module. I said earlier that the exports parts of accessibility is pretty straightforward. A package is either exported or it's not. Well, it's a little more subtle than that, it turns out. Here are some of the exports of the java.base module. Exporting a package means that anyone can compile and run against its public types. There are dozens more packages in java.base that are not exported. No one can compile against their public types. Even if you make a class file by hand that refers to a public type in a non-exported package, it won't run. But that's accessibility in the Java language in VM, where the accessing class and the target class are known statically. What about accessibility with reflection, where the target class is only known dynamically? We think it's very important that exporting a package such as java.security for static access does not mean that anyone can reflect over the internals of that package, because history has shown that if they can, they will. Here's a Stack Overflow question from July of 2016. Someone was using setAccessible to access a private field in the class java.security.keystore. The purpose of this class is, and I quote, a storage facility for cryptographic keys and certificates. If ever there was a class whose private fields should be inaccessible, this is probably the one. The Java security package is exported so you can code against the public type keystore, not so that you can reflect over keystore's internals. So just exporting a package does not allow reflection to access the non-public elements of the package. Public elements, no problem. Non-public, If you obtain a class object for a non-public type in the package, you can still list its members, but you cannot call get or set on its java.lang reflect field objects, even for a public field. Nor can you call invoke on its java.lang reflect method objects, even if a method is public. Similarly, if you obtain a Java lang reflect field object for a private field in a public type, you cannot call get or set on it. Even calling setAccessible will not help. If the author of a module really wants to allow access to non-public elements via reflection, this can be expressed with a second directive, and that's called opens. You can open packages one by one, as shown here, or you can open an entire module by putting the open token, using open as a modifier on the module keyword itself. This allows reflection to work as it did in Java 8. Private members of public types can be accessed, and public members of private members of public types can be accessed, and as well as even private members of non-public types. We don't officially call this weak encapsulation, but you can think of it that way. The bottom line here is that strong encapsulation is even stronger than the powerful reflection capabilities traditionally offered in the Java platform. It's up to the module author to choose strong encapsulation, and if they do, there's no way for another module to break in. The module system API does not allow one module to augment the exports of another module reflectively. A module can only export its own packages via the API. So that's accessibility and readability. Accessibility used to be a simple check for public or same package. In Java 9, accessibility strongly encapsulates module internals. Accessibility relies on readability, which can be direct or implied, and, big point, accessibility is forced by the compiler, by the virtual machine, and by the reflection API. Part 2, different kinds of modules. Everything so far has been about named modules, modules explicitly declared with a name in a moduleInfo.java file. Now, what about jar files on the class path that don't have a moduleInfo.class file? They seem to be off in some weird world of their own. To keep the model of accessibility and readability consistent, we introduced a concept of the unnamed module. All classes not in named modules are in the unnamed module. It's as if everything on the class path is in one big happy module. Because it's a module, we can ask two questions. What does it read, and what does it export? What it reads is very simple. It reads every named module, all of them, as if by magic, for free. This means anything exported by a named module can be accessed by the unnamed module. You can turn a jar file into a named module by adding a moduleInfo.class and putting the jar on the module path where named modules are found. Jars left on the class path will not realize that anything happened. That's a big help for migration. The next question is, well, what does the unnamed module export? Before that, though, we should ask, who reads the unnamed module? Remember, our goal in the module system is reliable configuration. We believe very strongly that named modules should not read the unnamed module out of the box. It would make a complete mockery of reliable configuration to let named modules depend on the arbitrary chaotic content of the class path. So you cannot write something like requires unnamed or requires class path in a moduleInfo.java file. There are no reads edges going out to the unnamed module. Of course, this is a huge hindrance for migration because any jar you turn into a named module can't access the other jars that are left on the class path. The solution to that problem is automatic modules. You can take a jar, say guava.jar, and now move it from the class path to the module path. This turns the jar into an automatic module. That's all you have to do. You certainly don't change the contents of that jar file. An automatic module is a named module declared implicitly rather than explicitly. Its name is derived from the jar file name in a very obvious way. Placing guava.jar on the module path will get you an automatic module called guava, oddly enough. As before, whenever you see a module, you should ask, what does it read? What does it export? The automatic module guava reads everything in the JDK and the unnamed module. It's as if it says requires unnamed. Now the hindrance to migration is gone. You can turn a jar into an automatic module and it can still access the jars left on the class path. We asked earlier what the unnamed module exports. The answer is all of its packages. in junit.jar and glassfish.jar and hibernate.jar precisely to help code that's been moved up to automatic modules, which need to read the unnamed module. Because an automatic module is a real named module, another named module can require it. Suppose the myapp module says requires Guava. So there's a reads edge from myapp to Guava. What does an automatic module like Guava export? That's easy, all of its packages. So myapp can access all of the public Guava types. Myapp could even say requires transitive Guava in order to transmit its dependency on Guava up to its own consumers. So anyone who reads myapp would read Guava for free. So by moving a jar from the class path to the module path, you get an automatic module that lets you start building up your own graph of modules. It's not necessary to wait for every jar in the class path to be modularized by its author, might be somebody completely different, before you start developing modules that require it. So there are three kinds of modules. We have explicit named modules, such as java.sql. We have automatic named modules, such as Guava. And we have the unnamed module, which is where everything from the class path goes. And between all these different kinds of modules, there's lots of readability inserted by the module system for free to help with migration. Part 3, loaders and layers. I said before that strong encapsulation is independent of class loaders. This means that the model of class loading in Java 9 is unchanged. The mechanism of loader constraints is unchanged. The notion of runtime packages is unchanged. The Java Lang class loader API is essentially unchanged. So in case you haven't gotten the message, class loading doesn't change. In addition, the actual class loaders in JDK 9 are unchanged from JDK 8. We have the bootstrap loader, we have the platform loader, formerly known as the extension loader, and the application loader, sometimes called the system loader. Traditionally, the vast majority of JDK classes were defined by the bootstrap loader. Critical JDK modules such as java.base still have their classes loaded by that loader. For non-critical modules, however, it's important for security to move their classes out of the bootstrap loader. Modules in the bootstrap loader run with all permissions, which is not ideal from a security perspective. They can only be deprivileged, that is, run with fewer permissions, if they're not in the bootstrap loader. Therefore, in JDK 9, all the modules containing Java EE technologies, such as Java.Corba, have been moved, as well as the JDBC modules, Java.SQL and JavaSQL Rowset. Their classes are now loaded by the platform loader. Frankly, moving a module as big as Java.Corba, 1,831 classes and 31 exported packages, is no small accomplishment. This deprivileging work will continue for other modules for a few years yet. The application loader is responsible for everything else. A number of JDK tool modules, such as JDK.compiler, have their classes defined by the application loader. All classes in modules on the module path, whether they're in a modular jar or in an automatic module like Guava from before, are also defined by the application loader. And finally, all classes on the class path in traditional jar files, such as junit.jar and glassfish.jar in our example, are loaded by the application loader. A couple of notes on compatibility. First, frameworks that delegate directly to the bootstrap loader to find JDK classes might break on JDK 9, because many JDK classes aren't there anymore. Frameworks should use the new class loader method getPlatformClassLoader, which returns a loader guaranteed to provide visibility of exported JDK classes. Second, the application loader is no longer an instance of URL class loader. This was never mandated by the specification, but it was true in practice. Some frameworks assume that it is in order to hack into its add URL method, and these break on JDK 9. Some of them have already been fixed. The only supported way to dynamically extend the class path is with the class path attribute in jar files or with the agent API in Java Lang instrument. Now, you might be wondering where the module system itself fits in this class loading story. Before I answer that, though, it's important to realize where the module system isn't. Module systems that have been built for the Java platform so far are, well, they're basically sophisticated ways to build networks of class loaders. They create loaders that define classes found in modular artifacts, and the loaders delegate to each other in accordance to some kind of modular imports and exports. As I mentioned before, there's some encapsulation for classes because the loaders can hide classes from each other, but it's kind of a weak encapsulation. It's not all that strong. A module system that works in this way will still run on JDK 9 because class loading hasn't changed. This is one of the big reasons why we tried really hard not to change class loading. However, the module system in JDK 9 is quite different. The module system in JDK 9 and Java 9 is not a factory for class loaders, but rather a conduit that allows modules to be communicated to the virtual machine. Whoever creates the class loaders is responsible for using the module system API to transmit module names and contents and dependencies and exports to the VM. That's how the VM knows enough to enforce accessibility. It's also how the core reflection API can enforce accessibility, since it's based upon the VM-provided class objects. You can think of the Java launcher as creating 3 loaders and doing the transmission for modules on the class path. Now, you can see why we wanted the module system to be disinterested in class loaders. The JDK has been factored into dozens of modules, but its class loading architecture has not changed. Encapsulation is provided by true VM-level accessibility, not by class loader-based visibility. So the module system doesn't need to mandate 1 loader per module. It can handle multiple modules per loader just fine. You'll recall I talked earlier about the unnamed module as a vehicle for compatibility. Strictly speaking, I was referring to the unnamed module of the application class loader. In fact, every loader has its own unique unnamed module. If the VM sees a class being defined by a loader and the VM can't associate that class with a named module that was transmitted earlier, then the VM treats the class as being in the loader's unnamed module. As you might guess, the VM always allows access to public classes in one of these unnamed modules. This all means that if every class is a member of this all means that every class is a member of a module. Even classes in the jar files on the class path, junit.jar and glassfish.jar, are members of a module. The seventh blue box in the VM on the right. The blue box didn't make it, sorry. If you have a class object, the getModule method will always return a module object, is the main point. The module system introduces the concept of a layer to associate loaders with module. A layer is a family of class loaders that serve together to load classes for a graph of modules. Logically, the Java launcher defines the boot layer consisting of the 3 familiar loaders shown here. It's the boot layer that associates the java.base and java.logging modules with the bootstrap loader, java.sql and java.corba with the platform loader, and so on. A layer is created from 2 things, a graph of modules and a function that maps modules to loaders. Layers are in fact quite lightweight. On the left is the graph from resolving the jdk.jlink module, which contains the jlink tool for building runtime JDK images. On the right is a Lambda expression mapping modules to the bootstrap loader and the application loader. Creating a layer informs the module system about the packages that will exist in the program and the modules they'll come from. The module system passes this information to the VM so that when classes are eventually loaded, the VM knows which module a class belongs to and what that module reads and exports. It's like the VM has kind of a shadow copy of the module graph that it uses when checking accessibility between classes. Because of how class loading works, the module system must enforce certain constraints on a layer's module graph and on a layer's mapping from modules to loaders. Let's talk about the graph first. This is the graph of standard modules in JDK 9. What do you notice about this graph? It has a key property. Anyone?
No cycles.
No cycles, bingo. There are no cycles. This is the first and biggest constraint on a module graph. It's taken almost a decade to untangle the tens of thousands of classes in the JDK to the acyclic and relatively sane state you see here. And after all that work, we would like to keep it that way. In fact, one of the motivations for investing in modularization of a code base is the knowledge that once complete, there won't be any backsliding into the ball of mud that cyclic dependencies allow. We are not the only people who think this. Java Application Architecture is an outstanding book about modularity. Highly recommend it. In a section titled Cyclic Dependencies, the Death Knell, it says, excessive dependencies are bad, but cyclic dependencies are especially bad. The book goes on to say, generally speaking, cycles are always bad. However, some cycles are worse than others. Cycles among classes are tolerable, assuming they don't cause cycles among the packages or modules containing them. Cycles among packages may also be tolerable, assuming they don't cause cycles among the modules containing them. Module relationships must never be cyclic. So that's very clear, right? Let's turn to the other constraint on module graphs. The second constraint on the module graph is that a module must read only one module that exports a package called P. If a module could read more than one module that exports P, and as X is trying to do here, in which module would P be accessed? There's no answer. The module graph is just broken. So we defend against that. Only module graphs which obey this constraint and have no cycles can be turned into a layer. This is really what we mean, in essence, by reliable configuration. Configuration is reliable when a module can access only one version of a package at a time. There are no split packages, such as you get when multiple jars on the class path contain potentially different versions of the same package. Now, you might wonder if it's possible for X to read version 1 of Y, while at the same time another module reads version 2 of Y. After all, X and the other module would each read only one module exporting P. The answer is that it's not possible, because it can only work safely in certain scenarios. And outside of those scenarios, it's far from clear that supporting it out of the box is worth the complexity. Recall that a layer includes a module graph for which we saw two constraints and a mapping from modules to loaders. The main constraint on the mapping is that if different modules in the graph have a class called C, then those modules must be mapped to different loaders. This is due to a fundamental limit in class loading. A class loading can only create one class called C. More conservatively, we say that if different modules have the same package, not just class, then those modules must be mapped to different loaders. The mapping from modules to loaders has another constraint that's not practical to check because it concerns how the loaders behave at runtime. It's that loaders must delegate to each other in accordance with the reads edges in the module graph. Now, the reason for this is obvious. If module X reads module Y, then in order for X's classes in one loader to access Y's classes in another loader, X's loader must have enough information to know to delegate to Y's loader. As their name suggests, layers can be layered, like pancakes or waffles. When a graph of modules is resolved, it's actually resolved against a parent layer. In fact, you can now have, with a recent change, it can have more than one parent. Thus, then when the graph helps to create a new layer, the new layer picks up the parent layer. This allows a graph of module to have what are almost dangling references, that is, requires clauses for modules that the module system will find in a parent layer during resolution. Now, on the left here, resolution has set up not only a reads edge between modules in one layer, but also a reads edge between modules in different layers. Constructing a tree of layers in this fashion is the job of a framework, such as an app server or a test harness. Layers give frameworks tremendous freedom to organize modules at runtime without upsetting the framework's traditional use of class loaders. It's a lot like the invoke dynamic instruction in Java 7. It's a way for framework developers to interact with the VM on a fairly intimate basis to reify information about the shape of the program. Let's look at one scenario where layers help out. Layers are how the module system supports multiple versions of a module. Here, an app server has created two layers on top of the boot layer. On the left, the Hadoop layer reifies a module graph with Guava version 11 and Jackson version 1. On the right, the JavaScript layer reifies a module graph with Guava version 18 and Jackson version 2. Each module graph is well formed and mapped to loaders in a sensible way, but the modules in the Hadoop layer are not aware of the modules in the JavaScript layer and vice versa. But note, this is all thanks to a framework creating the Hadoop and JavaScript layers in the first place. The Java launcher does not create layers such as this. All it does is resolve the modules you give on the command line, then map everything in the resulting module graph to the application loader in the boot layer. It supports only one version of each module. The reason for that is to avoid the nightmarish problems that occur when multiple versions of a module casually come into contact with each other. It's really only safe to use multiple versions of a module when a framework such as an app server is in control. The takeaway is this: just as modules wrap up coherent sets of packages and interact with the VM's accessibility mechanism, layers wrap up coherent sets of modules and interact with the class loader visibility mechanism. It will be up to frameworks to make use of layers in the next 20 years, just as they made use of class loaders in the first 20 years. So that was a deep dive into loaders and layers. Modules do a better job of encapsulation than class loaders, but class loaders are still around. They're still very necessary. Layers control the relationship between modules and loaders. Assuming that class loaders respect the module graph, a system that you build is safe by construction. There will not be cycles. There will not be split packages. Now, zooming all the way out, here are 3 key points. The module system provides strong encapsulation of modules by the compiler, the virtual machine, and core reflection. Unnamed and automatic modules help with migration, and the system is safe by construction, as I just said. In essence, the module system is a seatbelt. It's not a jetpack. If this reminds you of the rationale for generics, well, you're right. Writing a module declaration makes your code more reliable and maintainable, much as writing list of string makes your code more maintainable than simply writing list. You always knew that your list held strings, and generics let you say that. You always knew that a package was not for general use, and modules let you say that. It's no coincidence that designing a practical module system and modularizing the JDK has taken approximately as long as designing the generic type system and generifying the JDK. Part 4, the road ahead. It's still quite long. Although the module system is conceptually simple, there are changes in Java 9 that probably won't break user code but might break framework code. I'd like to go through them quickly. There are 3 areas of incompatibility in JDK 9 connected with the official definition of the Java SE platform. First, we've removed 6 methods from Java util logging and Java util jar. For the first time ever, we've actually removed things. The signatures of these methods made the Java base module depend on the Java desktop module, and nobody wants that. This removal was announced in the Umbrella JSR for Java SE 8 in 2014. Yes, this has been a very long-term project. In addition, we've removed 2 AWT packages that were never supported despite the fact that they were in the java.star namespace. Second, the Java EE types shipped with the JDK are not accessible by default. Don't worry, they're there. This means Corba, JaxB, JaxWS, the Java Activation Framework, and the JDK subsets of the Java Transaction API and the Common Annotation API are not accessible by default. The types are physically in the JDK image, but their modules are not read by the unnamed module. If you're writing a module, no problem. You just require java.corba or java.xml.bind or whatever. But if you're running code from the class path, you need to use a command line flag to activate EE modules. Now, this is not meant with any hostility towards Java EE technologies. In fact, that we chose to do this to make it easier to interoperate with existing copies of those technologies, many of which are not actually in the JDK. Third, and finally, the version strings reported by system properties have changed. Code that looks for 1 dot at the beginning of the string will fail on JDK 9. Sorry. There are three areas of incompatibility within the JDK implementation. First, we've slimmed down the SunMISC package. SunMISC unsafe is still accessible, but SunMISC base64 encoder and base64 decoder are gone. One thing you can do today is run the JDEPS tool that came in JDK 8 over all of your jars. There's actually a better version of JDEPS in JDK 9 early access builds. It will tell you if they're using unofficial classes such as SunMISC base64 encoder, and then recommend supported replacements such as java.util.base64, an API introduced back in Java 8. Second, almost all JDK internal APIs are not exported. Code that tries to access types in the sun.net.ww package, or sun.security.x509, or com.sun.org.apaches.xerxes.internal.jaxp, I could go on and on about this, will fail with an illegal access error. The only way to regain access is with a command line flag. At least it's possible. Third, many internal aspects of the JDK have been overhauled, such as the layout on disk and the implementations of its class loaders. Code that assumes there's a file called rt.jar or tools.jar in a particular directory will fail because those files no longer exist. Scripts that try to patch the JDK with -x boot class path /p will fail on JDK 9 because that flag is no longer supported. And as I mentioned before, code that assumes the application loader is a URL class loader or that assumes all JDK classes are defined by the bootstrap loader will fail on JDK 9. The module system tries very hard to support migration, but it takes only one unmaintained library to prevent migration to JDK 9. If that library cannot migrate, nor can anything on the, if that library can't migrate, then neither can anything on top of it. In this regard, modules are unusual. They suffer from a tragedy of the commons kind of problem, whereas most big features like generics or lambdas let people opt in at their own pace without needing to wait for others. So, preparing for JDK 9. The single best thing you can do is fire up JDK 8 and run the JDEPS tool, which analyzes dependencies. Actually, the single best thing you can do is run JDEPS from a JDK 9 early access build. But if you happen to have 8 already, that'll be the second best thing. It can tell you if your code or the code you rely on will be affected by changes in JDK 9. Please try the EA binaries on jdk9.java.net. The module system has been present and active in these binaries since March of 2016. Plus, everything you ever wanted to know about the module system is discussed in JEP 261. I can't emphasize enough how much valuable information is in that JEP. There's also JEP 260, which defines the JDK internal classes exposed in JDK 9. There are still a few of them, SunMISC unsafe. And JEP 223, which defines the new version strings beginning with 9, and JEP 220, which describes how rt.jar has gone away and what it has been replaced with. Finally, JEP 200 gives an overview of the JDK modules, but if you've already read JEP 261, there won't be any surprises. So there are direct links to all of these JEPs from the Jigsaw project page shown there. I work for Oracle. Don't believe a word I say. Thank you very much. We have about 12 minutes for questions. There's a microphone up there on the stand. Please use that. Or if you like, you could tweet at me and I'll read questions off of Twitter. Any questions? No questions.
One question.
Yes,
in this dependency graph, it seems that everything, or lots of things, have a dependency on this Java logging module. Why is that? Is that just a transitive dependency?
Good question. Let me roll back. Show navigator to the graph. Where's the graph? In that graph, there are two types of edges. I will find it somewhere. Okay, sorry, let me pop out of this. There it is. Okay, in this graph, there are two kinds of edges. Well, sorry, I lied. There are three. The solid edges represent requires transitive, so they transmit the API to the consumer. The dashed edges are merely for implementation. So Java, if you look at the API of java.security.sazzle, you won't see any logging types in its API, so it's a dashed edge. Most of the edges going into java.logging are dashed. The ones that are solid represent uses of the Java logging API and the API of the upper module. So in many cases, the use of java.logging is just an implementation detail. In other cases, it's essentially reusing the API and expecting the consumer to use the API.
Java 9 has been postponed several times already.
Yeah,
so
it's software.
My question is it's actually not strictly related to the Jigsaw, but how likely is it from your point of view that the current schedule will actually stay?
I'd say the probability is it's somewhere between 0 and 100%. You know, I could rant about estimation in software projects. It's just fundamentally impossible. It's an impossible thing. You make an estimate, you do the best you can, and if you wind up needing more time to do the right thing, then you take more time. You know, we're not going to saddle the ecosystem with something that's broken just in order to hit some arbitrary deadline. That would be stupid. Another question?
Yes. I was left with the impression that the opens keyword needed a bit more explanation.
You were under the impression the opens keyword needed a bit more explanation. Do you have a specific question I could answer?
Just how it works, what it does. How can you open another module?
Well, opening is not about opening another module. It's about you can only a module can only open itself, right? You can open a specific package or a set of specific packages, or you can open the entire module, which opens all of its packages. And all that open means is when a package is open, that means that at runtime, all of its public types are accessible, and all of its non-public types are also accessible if code using reflection to get to them goes to the trouble of invoking the setAccessible method. That's what open means.
Right, but I was talking about the opens keyword. You spoke of an opens.
Right. Okay. So I can open every package in a module by writing open module name and then curly braces and stuff. Right. If I don't write that, then in a normal strong module, maybe I have 5 packages I export, 12 packages that are completely internal and I don't export, and then 1 package that contains Pojo classes that Hibernate's going to play with. Right. I can say opens just that package. Does that make sense?
No, but never mind.
Okay, sorry. I mean, feel free to come down later. This is probably
Yes.
just some simple miscommunication thing.
I have a bit of an abuse question.
A bit of an abuse question?
Yes.
Is that right?
About Java abuse. I tend to notice in my work that a lot of code I rely on is not explicitly written as a library.
Yeah, we've seen that.
So basically, what people do is they make everything private, and only things that they happen to use themselves, they make public somewhere because they need it somewhere else.
Mm-hmm.
And I kind of foresee that the same thing is going to happen with the modules. And I was wondering what your thoughts are on that.
So it sounds like you're worried that if the author of a module is lazy, they'll just decide, oh, I'm just going to export everything and open everything. I don't have time to think about this.
Well, actually, the other part around.
The other way around?
The people only open up stuff they need themselves in other packages or something within their module.
Okay, well, it sounds like they're being perfectly sensible. What's the problem?
The problem is that they might not think enough about their public API and therefore not go through enough lengths to
Well,
expose it.
then they need to be educated.
Yes.
Right. So there's definitely a shift here. The module system gives module authors, both power and responsibility, as we say. Right. You have the power to strongly encapsulate internals, but because the module system enforces strong encapsulation, it's essentially impossible for ordinary code operating in ordinary ways to break into that. So if you're the author of the module, you have more motivation to think carefully about what your API is and what your API isn't. And if you get it wrong, your users will be unhappy, and hopefully they'll file bugs or submit patches or pull requests or whatever to help you out. But ultimately, if something's broken in that way, that's not something that they can fix by just fussing with the jar file or something.
Let's hope people take responsibility.
At the end of the day, you just have to hope that people will do the right thing once they're educated, and sometimes that assumption turns out not to be true. Please.
What impact do you see on unit tests and frameworks? Common unit test pattern being you put the test class in the same package as the tested class, thereby gaining access to package and protected members, and otherwise unit frameworks that do all kinds of nasty stuff.
Yeah, no, there are mechanisms to handle all of that. There's a command line flag that will let you essentially patch the content of a module. You can insert stuff in, and our own JTReg unit test framework uses that already. We've had some discussions with other test framework authors, and they know about that and they're thinking about it. And hopefully they'll upgrade to use that. So yeah, all the usual testing scenarios. Hopefully we've tried to think through. If we've missed one, please let us know. Okay, quick question on Twitter. Someone very observant wondered, why is there JDK HTTP server in that module graph? Well, it's because we are honest. Okay, this module graph is the same graph I showed in the keynote. You might notice it's not as pretty as ones I've shown in the past. The reason for that is that it's mechanically generated. When you do a JDK9 build, you get, amongst the many things you get, there's a directory full of dot files that show the graphical structure of logical subsets of the platform. This is the dot file rendered into a ping of all of the standard modules, and JDK HTTP server is just happens to be an implementation dependence of java.xml.ws. All of the other modules would show up if we started showing the JDK modules themselves. They don't show up here because, for the most part, they're related through the service mechanism, which is something that would be another talk to explain. But maybe next year I'll do that talk. All right, 2 minutes, 30 seconds. Go.
Hopefully, quick question. Is open for introspection the same as open for the debugger?
Is open for introspection the same as open for the debugger? No, because if you're a debugger, you can already get into everything. Right? That's like the one big loophole through which you can drive a truck. Intentionally is if you're using a debugger, well, you should be able to poke into anything because, well, that's what debuggers do. Okay. So of course you can.
Clear.
Question on Twitter: why no recursive package exports? I don't even know what a recursive package export would be. Is there another quick question? I mean, if you ask that question, feel free to come down and ask me when we're done.
One short question. Why the visibility rules don't apply to protected packages?
Why do the visibility rules not apply?
In one of the first slides, you showed that the public will be impacted by the export. Does the same rule apply to export protected?
The protected access mode is its own sea of despair. The complexity required to explain the protected access mode in both the JLS and the VM spec is, basically, whenever I talk to Alex Buckley, who maintains those specs, whenever I talk to him about this, he just, it's total sad face. Because it's hideously complex, and for that reason, I just don't talk about it in these talks. I could do a whole nother talk on on protected and how that works with accessibility. We've tried to work it out as logically as we can, but maybe we got it wrong. If we did, let us know, and time is up. Thank you very much.